In section 4 of chapter 17, we will be discussing Gibbs free energy. Learning target-wise, we'll be looking at if a process is spontaneous or thermodynamically favored by being able to calculate or talk about qualitatively the signs for the enthalpy change and the entropy change, and then calculate or estimate the Gibbs free energy change. For Gibbs free energy or free energy, we use a capital letter G. It is the amount of work that can be done by a spontaneous process. We can calculate the change in free energy using this equation right here. The sign of delta G can tell us if we have a spontaneous process or not. Remember, in an earlier section of this chapter, we talked about the sign of the entropy change for the universe to determine if a process was spontaneous or not. Usually delta G is going to be more useful. The nice thing about this equation, it takes two state functions, enthalpy and entropy, and kind of combines them together into a single state function that can determine if we have a spontaneous reaction. This equation is also useful in dealing with temperature-dependent spontaneity, and you actually see temperature here as part of the equation. Now, let's take this equation and divide by -t. Now, you may remember from an earlier section in this chapter, negative delta H over T was equal to the entropy change for the surroundings. And over here, the negative T's are going to cancel. That leaves plus delta S, and that is always for the system. So remember, the entropy change for the surroundings plus the entropy change for the system is equal to the entropy change in the universe. So that gives us this. The entropy change for the universe is equal to negative delta G over T at a constant temperature and pressure. We said earlier that we wanted to see a positive entropy change for the universe for a process to be spontaneous. This means that delta G needs to be negative. We're looking for a decrease in free energy when we have a spontaneous process. If your delta G is positive, that means the reverse process is spontaneous. And if your delta G is ever 0, that means your system is at equilibrium. So let's think about the different signs that we can have for the entropy change and the enthalpy change, and what kind of sign we would then get for the free energy change, delta G. If your entropy change is positive and your enthalpy change is negative, we will get a negative delta G all the time, independent of temperature. So our delta H is negative, and then our delta S is positive. We are subtracting a positive number, so it will always give us a negative answer, a negative delta G. However, if we have our delta S negative and our delta H positive, then we will never get a negative delta G. We have a positive delta H, we're subtracting a negative delta S, so subtracting a negative means we are adding, right? And we will always get a positive delta G. So if we looked at the reverse process, that would again be negative and spontaneous at all temperatures. Now if we have two positives or two negatives, temperature is really going to play a part here. If we have a positive delta H, can the temperature be high enough to make this term larger than the delta H? And if it is high enough, then we do get a negative delta G and we do get a spontaneous process. Here it says where exothermicity is unimportant. That means where heat being released is unimportant. Now for the other case here, your delta S negative and your delta H negative, again, when you subtract a negative number here, you are basically adding. And so if the temperature is low, that term will be low enough to give you a negative answer for your delta G. This right here says where exothermicity is dominant, meaning where heat released is dominant. And we see that here with our negative delta H. This chart here is looking at ice turning into liquid water or melting. And it's at 3 different temperatures, -10, 0, and +10 degrees Celsius. Take a look at this column right here where delta G has been calculated. It is negative at 10 degrees Celsius. So spontaneous at 10 degrees Celsius. Does ice spontaneously melt at 10 degrees Celsius? Absolutely. It does not spontaneously melt at -10 degrees Celsius. At 0 degrees Celsius, delta G is 0, or is at equilibrium. The water is going through the process of melting. Both states coexist at equilibrium. Let's take a look at some of the other columns, like the enthalpy change. At all temperatures, it's the same and positive. This is an endothermic process. Take a look at the entropy column. As the water goes from solid to liquid, it is becoming more disorganized. Entropy is increasing. The entropy change in the surroundings is calculated here. All are negative because this is, again, an endothermic process. Heat is leaving the surroundings and going into the system. So that is a decrease in our entropy. Because there is a decrease in the random motion of the atoms, particles in the surroundings. The entropy change for the universe has been calculated here using the previous information there in the table. And you can see for the spontaneous temperature, 10 degrees Celsius, we see a positive value here and a negative value here at -10 degrees Celsius, where it is not spontaneous. This final column here is just the temperature in Kelvin times the entropy change for the system so that the delta G can be calculated. Finally, let's think about a liquid boiling. So we're talking about going from a liquid to a gas. The enthalpy change is positive. We need some heat to turn a liquid into a gas. The entropy change would also be positive as we are going from liquid to gas. The gases are more disordered, more random than the liquid. The entropy change for the surroundings is negative as this is an endothermic process. Heat is pulled from the surroundings into the system, and that decreases the random motion of those particles in the surroundings. So then when we think about delta G, we are at equilibrium at the boiling point. We have both phases existing until that phase change is complete. So our delta G is actually going to be 0.